So today we're going to be looking at a quadratic function. In the previous module, we looked at linear functions, and we talked about how linear functions, number one, make a line on the graph. But we also talked about the characteristics of the function itself being variables that are raised to the first power and not having any exponents that are higher than 1. When we talk about quadratics, what we're talking about is a function that does have an exponent, particularly the highest exponent, or what mathematicians call the degree of the function, is 2, meaning it has x squared as its highest exponent. It still doesn't have any funky stuff like a square root or an absolute value or a variable in a denominator. Those things are still not quadratics. They weren't linear either. Those are different types of functions. We're focusing in on quadratics now after learning about linear functions in the first module. So what we're going to do is we're going to take a look at first the standard form of a quadratic, and we're going to talk about how, particularly with the standard form, a lot of times you are given the equations in standard form if you're working in some type of situation that you need them. But then we're going to look at two other forms, in particular, Vertex Form and Intercept Form. And those two forms, you can actually kind of obtain those particular forms from some real-life context and just from a mathematics context. And you can still write your quadratic function into standard form even from those forms. So before we go in too deep about all three forms, which we will, let's look at what the standard form of a quadratic looks like. The standard form of a quadratic function is a function that can be written like this. F of x, or remember, we've talked about this probably before in that first module. F of x is kind of a fancy way to write y equals, so don't panic when you see that. That's the same concept that we talked about being in function form in the earlier module. Y equals ax squared plus bx plus c, where a is not equal to 0. The key thing that I'm trying to tell you there is that a function to be a quadratic has to have an x squared term. A lot of times some textbooks will call this the quadratic term. Notice that if it doesn't have the quadratic term, it is bx plus c, which should remind you of the mx plus b format for a slope-intercept form of a line. So a quadratic, essentially, it has to have a quadratic term, but it doesn't necessarily have to have this linear term or this constant term that's just a number right here. So this is called the standard form of a quadratic. The a and the b and the c just represent numbers in the function. An example would be something like this. Y equals 3x squared plus 2x minus 4. Mr. Harrison just gave you that one. I didn't ask you to come up with it. You didn't have to do anything to find it. I just gave it to you. And many times the standard form, when you're dealing with situations that use standard form, you probably are looking at some type of, if it's a job or if it's even just math class, you're looking at some situation where you are being given a function that talks about something, and then you're just analyzing what's happening. So the standard form, there's not a real quick, easy way to find a standard form equation just on your own, unless you're using some technology to help you. And I'm going to get back to that in just a little while. So I do want to mention a few things about the graphs of quadratics. I know that this lesson is not about graphing, but it's kind of hard to separate writing a quadratic equation from the graph, mainly because the quadratic equation has a very specific type of graph. Some of you may have heard of this word before, but every quadratic function has a U-shaped graph called a parabola. And I know that looks like parabola, but that is a parabola is the name of that graph. You may have heard somebody even say the word parabolic in shape. There are certain things out there in life that are similar to a parabolic shape, like the St. Louis Arch in Missouri. It's actually not a parabola, it's actually a catenary, but it's close. And then you have things like satellite dishes use the same type of technology as a parabola. And when you are looking at a parabola graph, it is a U-shaped graph. I'm going to show you what that looks like real quick. This would be the standard form of a quadratic y equals x squared. Notice that one doesn't have a bx term and it doesn't have a c term. So it doesn't have the linear term or the constant term, but it has the quadratic term and it makes this shape like this. Now in the next section, when we go to graph quadratics, we'll talk about why that's happening and get a little bit more detail. Basic idea is this: you're squaring the x, so you're ending up with the negative number. When you plug in a negative number, it becomes positive, and you're having some numbers that jump up pretty quickly when you square them. So you end up with this shape of this graph that's kind of this scoop at the bottom, and it kind of goes up pretty steep on the sides because of what's happening with the x to get the y. So that is the parabola. If the leading coefficient a out in front of that equation is positive, the parabola is going to open up. If it's negative, it's going to open down. Being open and honest with you, one of my favorite things to do with a quadratic equation is working on maximum revenue. And so when you are talking about a parabola that opens down, there is a point at the top that is a maximum point. That point has a name. It's called the vertex of the parabola. Now, you've probably heard the word vertex before, too, in reference to maybe some shapes in the corner of an angle. Sometimes it's called the vertex. So the vertex will be the highest point when you have that parabola that's opening down, and it will be the lowest point when you have a parabola that's opening up. So that is called the vertex. The reason I want to point a lot of this stuff out to you is because the vertex is an absolutely critical point on a parabola, and it will help us to find the equation of a parabola if we have the vertex and one other point, because these graphs are perfectly symmetric. And these graphs are a little different than the linear equations where we only needed 2 points. We technically need 3 points. Or we need the fact that we have the vertex, which is the middle point, and a point on one side to know that it's symmetric for the other side. I know I'm throwing a lot of information at you here, but we're going to practice actually finding some equations of these and thinking about the vertex helping us with that in a little bit when we talk about vertex form. So I want to focus in, first of all, on the standard form. One of the other things I want to make sure that you understand, like I said, about a parabola is that you do have this vertex in the middle, and you do have points that are symmetric on either side, like this. And so when you have a parabola, you need more than just 2 points to find the parabola. You need 2 points to make a line because it's a straight line. You can find that slope really quick. On a parabola, the slope changes the whole time this way, and it changes the whole time this way. You have a different slope everywhere on this line, or this curve, I should say. So when we talk about a parabola, we're going to focus in and we're going to learn a lot about this guy, the vertex. But we're going to also use other points, just like we did with finding the slope of a line and using another point to find the equation. We're going to do the same concept with parabolas as well. So I know, again, I'm going through a little long thing about the actual graph itself, even though this is not graphing today. It's just essential that you understand that the graphing and the writing equations tie very closely together on these. So, one of the things that you see with quadratic equations is you see things that are launched or thrown through the air. This particular example is about Natalia Lasovskaya. She holds the world record for the women's shot put. And actually, I think she might have been beat out recently, if I'm not mistaken. But the path that her record-breaking throw took through the air is modeled by this function. notice that this function is given to me. And this is what I was talking about a little while ago when I said a lot of times with the standard form of a quadratic function, the parabolic path or the parabolic shape, the actual equation is given to you. You don't have to actually figure it out a lot of times. You can, like I said, you have to have more than just 2 points. And we're going to look at how to do that with 3 points on Desmos here in just a little bit. So I'm going to let you use some technology. But this is the path of the ball. Because it has this x squared, and because this value in the front is negative, that tells me that essentially this ball is thrown from her hand through the air in a parabolic path until it hits the ground. Notice that this parabolic path is a little flat right here because we're talking about throwing a shot put through the air. It's not going to be a very steep curve on this. There are some things in life where we can see a very steep curve. There are some things where this parabolic shape is even wider and fatter, flatter, whatever you want to call it. I'll give you a kind of a simple, kind of goofy example, but it's a bullet that's shot out of a gun gets pulled down by gravity as soon as it leaves the gun. And so it follows a parabolic path, but it's really stretched out because of the speed of that bullet. So when you throw something or launch something through the air, it follows a parabolic path because of gravity. But the speed that it's thrown through the air also determines how far it's going to go up. Where it's let go from her hand also determines how far it's going to go up. There's a lot of things that go into this shape of this parabola. When we get into the graphs a little bit more next lesson, I'm going to talk about that in a little bit more detail. But think about this number right here specifically. We'll talk about him alone. That, remember, was the y-intercept when we were talking about linear equations, because it's when you plug in 0 for x. Guess what? It's also the y-intercept in this. So that means where she let the ball go. The other two numbers have to do with how gravity pulls down this negative and how the ball is actually launched through the air, this 0.9325. We're going to actually look at that later, maybe in this slideshow. So, as we go through and we look at a parabola, this is how an equation could be written for a quadratic. Again, this was given to you. And then later on in the graphing, we're going to talk about how do we find out how high this thing went, that maximum point, the vertex. How do we find out where it hits the ground? That's going to be things that we look at later in the chapter. So right now, I'm just kind of introducing you to the actual written form of a quadratic equation. Here's another example. On dry asphalt, the distance d in feet needed for a car to stop is given by d equals 0.05 s squared plus 1.1 s, where s is the car speed in miles per hour. What speed limit should be posted on a road where drivers round a corner and have 80 feet to come to a stop? So as the drivers come around this corner of maybe a mountain road, there's a stop sign right here, and they come around this corner. This right here to this right here is 80 feet. That's all they have to stop. This equation, again, was given to you. The distance is equal to this equation with speed over here. Well, if they have 80 feet to stop, 80 feet is the distance they have to stop. 0.05 s squared plus 1.1 s. And I apologize about my s's and my 5's looking very similar to each other. That would be an equation that we're going to learn how to solve later, that I could find the speed that that car should be traveling and put up a speed limit sign on the road. Who would actually use this? People who are in the Department of Transportation. I've also seen an article about state troopers in South Carolina using these types of equations to investigate a wreck. Because if this is the stopping distance that the car would stop in 80 feet, if they see skid marks and tire marks on a road when there's a wreck, they can figure out how fast the car was going. And weather conditions can be brought into this. This equation can be a little bit different if it's not dry asphalt, if it's gravel, or if it's wet asphalt, or it's ice. the equation becomes different and they can find out the speed that a car was traveling when it needed to stop. Or, like I said, they can make suggestions about speed limit when you deal with a road and you have a certain amount of space to stop. So we're going to learn how to solve this. But notice again that this equation was given to me. So there are a lot of times in this where there's been somebody who's already done the studying for me to get that equation. And here's another example of a quadratic equation that represents the amount of sugar produced from sugar beets. And again, it's kind of a goofy example, but the equation is given to you. Now, we are going to talk about this whole maximization thing when we talk about graphing a little bit next time. But thinking about, again, the shape of these graphs, because it's got a negative value here, and it's a quadratic, it's going to have a shape like this. That vertex is going to be that point that we're looking for. And as a business person, I can tell you, that's the goal. You want to try to maximize the amount of revenue that you bring in. Maximize your sales, whatever. So, that is one of the ways that you see the standard form of a quadratic is when you are given the equation. One of the other ways that you see a standard form of a quadratic is when you are given the format for an equation and you basically have to build the equation yourself. One of those that shows up in a physics context is something like particle motion, or when you're talking about launching something or throwing something, like I talked about a little bit earlier, the shot put example. You typically have the main part of the equation given to you. This negative 16t squared is how gravity is affecting the object's height over time in seconds. So every second, you're squaring it, and then you're multiplying it by negative 16. That is how that gravity is affecting the object when you throw it or launch it, or you drop something like a falling object. The h sub 0 is the initial height. That is where the object is thrown from, like the shot put we talked about earlier, or where it's launched from. If you've dropped something, a falling object is not going to have this initial velocity. But if you launch something, it's going to have an initial velocity times the time as well. Because typically you think about velocity, it's like feet per second. It's going to tell you how quickly something is launched through the air. If you have these types of problems, typically what you are given is you're given some type of situation that you're analyzing to see, if you're launching something, you want to know when it's going to hit the ground. You would take and first of all have to set it up. So notice this says a stunt man working on the set of a movie is to fall out of a window. So immediately think about this. Falling out of a window 100 feet above the ground. Notice that he's not being launched out of the window. So what you would have is the height for that stunt man is going to be negative 16t squared. And then you're going to have plus the initial height. So the gravity is affecting it, but you also have the initial height. So as time passes, he's going to go towards the ground. He's jumping out of a window and going towards the ground. Now, obviously, a stuntman is going to have some kind of pillow out. So this problem asks us, where is he? What is the time, before he reaches the cushion? And the cushion is going to be 9 feet high. So we want to find out when he reaches 9 feet for the height. Now, we're not going to solve that right now because we're just looking at how these equations get set up. We have the cushion that he's falling to from 100 feet, and then we are going to learn how to solve quadratic equations later. So I'm just showing you how these equations are set up right now. Now, that would be important time-wise because that also gives the cameraman and those that are running the cameras time to think about how they're going to set up, the types of green screen effects, explosions from the ground. If you're talking about a stunt man, maybe he was pushed out the window. When do we pan back up to the other window to see, who pushed him instead of, seeing the cushion that he lands on. Obviously, in the movie, you don't want to see that. You try to hide those things like that to make the movie look more realistic. Then you get into talking about, okay, what's the speed when he hits the ground and things like that, and that gets to even more equations. So that is standard form. There are two other useful forms for quadratics. One of those is vertex form, and the other is intercept form. Now, vertex form, we're going to focus in on as far as writing our equations here in just a second. The reason it is called vertex form is right here in the equation. These two numbers that you see, if you take the opposite of this guy and the same as this guy, or in other words, the opposite of the h and the same as the k, that is going to give me my vertex. That's why this is called vertex form. This number that's out in front is still going to make it open up if it's positive, open down if it's negative. In just a little bit, I'm also going to show you how this x minus h squared actually can look like the equations that we talked about in standard form. So I'm going to show you how those tie together as well. But that is vertex form. It's called vertex form because your vertex is staring you in the face. What we can do is we can use the vertex of a parabola and one other point, because a parabola has a symmetric shape. If we know one other point over here, we also know over here is going to be a mirror image. We can use a vertex and one other point to use vertex form and find our equation actually. Figure out which way it opens and find the value that how wide it opens or how skinny it opens. And we're going to talk about more details about the graphs next time. We also have intercept form. Now, next time we're going to get into the more specific reasoning behind the intercept form, because these two factors, we call them because they're multiplied together. That's what factors are. These two factors that are multiplied together are where we can get the intercepts of a parabola, meaning your graph could cross the x-axis in two places. Remember, the y-intercept right here actually comes from the standard form. I told you that just like the standard form, or the slope-intercept form, of an equation, this is the y-intercept. That's not what this one is. This is x-intercepts down here. And they're going to become very important for us. Specifically, it's where the y value of the function equals 0. And so they're going to become very important for us when it comes to solving quadratic equations. Right now, though, all we're going to see is some more real-life examples that have this sort of format like vertex form, intercept form. So now what we're going to do is we're going to take our two forms, these two other forms. I'm going to show you how they happen in certain situations. And I'm going to show you how they can also be transformed back to standard form. So let's take a look first at an example of writing an equation of a parabola. Now, I've already given you this parabola. Okay. Again, next time we're going to learn how to actually graph it as well. But remember what we talked about with a parabola. Number one, just like linear equations, the parabola has points on it. And these points, just like linear equations, are solutions to the equation. They're things that make the equation true. Specifically, too, we have this really special point on a parabola called the vertex. So anytime I know exactly where the vertex is, in this case it's 3, 4, I always, in that case, want to use that vertex form that I showed you on the other page, the x minus h squared plus k. Here's why. Because if I have the vertex, I know that this whole thing right here, the opposite of this number and the same as this number, will give me the vertex. I can go backwards. The opposite of 3 would mean inside the parentheses, I am going to have x minus 3 squared, because the opposite of negative 3 would be 3. And the same, I don't have to think about too much, there's going to be a plus 4. What I don't know is I don't know what this little a value is out in front. I do know, because this parabola opens down, we have talked about that, that means this is going to be a negative a value in front. So what I'm going to do is I'm going to take and try to get this a value. Well, just like I talked about with linear equations, we know what the vertex is, just like we knew what a slope of a line was. And we know that this graph crosses through a point. Here, here, even some of these down here. That looks kind of like an animal, doesn't it? So when you look at these points, like this one, let's say 2, 2, that's an x value and a y value that make the equation work. So that means it'd have to be equal everywhere. What you can do then is you can plug in 2 for y, 2 for x, and find out what a is by solving. So this is the exact same thing that we did when we looked at writing linear equations, and we plugged in the slope, and we plugged in another point to find the y-intercept, the beginning amount. It's the same concept. We plug in the vertex, we plug in another point on the parabola, and it'll help me get that a value. So then I can actually write my true equation. So I do some math here. 2 minus 3 is negative 1, but negative 1 squared is positive 1. So what is a times 1? That's just a. So this one's really nice to start off with. Then, how do I get a by itself? I subtract 4 from both sides to get a by itself, so that cancels. 2 minus 4 is negative 2. That means my vertex is 3, 4, and my a value for this equation is negative 2. That means my final answer would be y equals negative 2 times x minus 3 squared plus 4. And we're going to talk about how we can go backwards and actually get the graph from the equation next time. We are practicing just writing the equations this time. So this equation is the equation of a parabola. And it's using the vertex and another point. So if you have the vertex, use the vertex form and another point to help you get it. Now what I also want to show you is I want to show you how this negative 2 times x minus 3 squared plus 4, I want to show you how that ties back with the standard form of a quadratic. X minus 3 squared is really x minus 3 times x minus 3. Be careful there. You can't do x squared and 3 squared. That's not the same thing. Some of you may remember from some pre-algebra stuff that if you have these two parentheses like this, you can multiply them together using something called the FOIL method. The FOIL method is a way of multiplying two parentheses together that have two terms inside the parentheses. I think I even have one of those. Yeah, I have one right here. The FOIL method is multiplying the first terms in each parentheses, the outside terms of the whole problem, the inside terms of the whole problem, and the last terms of the whole problem. In each parenthesis, sorry. When you do that, what it does is it multiplies x times x. X times x is x squared. That's why this is a quadratic. X times negative 3 is a negative 3x. Negative 3 times x, that's the inside part, the I part of the FOIL method. And then negative 3 times negative 3, that's the last one times the last one. That's a positive 9. Notice what it gives me is it gives me this negative 2 out in front still, times x squared minus 6x plus 9. Notice that the x squared came from the x and the x, the first ones. The 9 came from the negative 3 times the negative 3, the last ones. But the negative 6x in the middle comes from a little combination of both. But now, if I distribute this negative 2 to all three of these, it gives me negative 2x squared, positive 12x, negative 2 times 9 is negative 18, plus 4, and I can add the plus 4 to the negative 18, and now I have minus 14. Now this is standard form. So vertex form, standard form. Now I'll go ahead and tell you, typically for most situations, if you have vertex form, you don't really want to put it in standard form. Typically you want to keep it in vertex form because the vertex is staring you in the face pretty much. So why would I want to put it in standard form? There is some things that we do with solving equations where we may need to get it in the standard form before we can solve. So that's one of the reasons why we still practice this. So let's do another one. So notice I have, again, my vertex here. I also have another point here and another point here. I have another point up here and another point up here. I've got several points on the parabola. But the key thing I have, again, is the vertex. So what is the vertex? The vertex is 2, negative 5. So vertex form says if I have 2, negative 5, I know I'm going to have something out in front multiplied by x minus 2, because it's the opposite, and then minus 5. Sorry, I forgot to tell you. The squared part too. And then minus 5, because the same. Opposite, same is your vertex. Now, technically what's happening there, we're going to talk about it when we get to the graphing stuff, but technically what's happening is the minus 2 and the minus 5 are actually moving the graph. It's sliding the parabola around. That's why it's opposite and same. It's actually moving it. Now, I would use this point right here just because it's an easy one, 0, negative 3. So negative 3 is the y value, 0 is the x value, and then I can solve this to find a. Again, what we're doing is plugging in what we don't know. Excuse me, we're plugging in what we do know to find what we don't know. So 0 minus 2 is negative 2. We square negative 2, and that gives me a positive 4. You can use your calculator if you need to. Then I add this 5. Add this 5. That's going to be 2. But I have a times 4, or you could put 4a. But to get rid of the 4, we divide by 4. 2 divided by 4 is 1/2. Now, what that means, and you can't see it really well on this one, but if you kind of compare it back to that first one we did a minute ago, this graph is a little bit wider. See how it's opened up a little wider? That's because this 1/2 is going to do that. We're going to talk about that, like I said, in a little bit more detail on the graphing video. So my a value is 1/2. Then I have x minus 2 squared minus 5. And you could do this multiplication thing again if you needed standard form. But if I don't ask you for standard form, you don't have to get it. This is still a quadratic. You just wrote a quadratic. All right. Now, let's talk about that FOIL method one more time. And then we're going to talk about the ones that look kind of like intercept form. So the FOIL method says, again, multiply the first term times the first term. So x times x is x squared. The outside terms of the problem, let's do this. Let's go a different color here. So that's x times 5, which is 5x. And then the inside terms of the problem, negative 4 times x is negative 4x. And then the last one here times the last one there, negative 4 times 5 is negative 20. That is, like we said, first, outside, inside, and last. When you collect your like terms here, you end up with y equals x squared. 5x and negative 4x is 1x, and then minus 20. There's that standard form of a quadratic. So that's taking this, technically, what we call intercept form. Notice that's those two factors like we talked about over here, the two factors that make intercept form, because they will help us out with finding the x-intercepts later on. So we take those two factors and we multiply them together and we get standard form. Again, the benefits there will be some things that we do with solving. One other benefit that we're going to look at here is that I'm going to go backwards sometimes and do a process called factoring. And factoring is splitting this back apart into the smaller linear parentheses. Because what that does is that in the solving methods gives me a way to break a quadratic down to easier pieces. We'll deal with that a little bit later, but I do want to point out that the x squared comes from the x times the x, the first one times the first one. The negative 20 comes from the negative 4 times the 5. That's all 4 spots. But the 1x in the middle comes from the 5x on the outside and the negative 4x on the inside to give me 1x. That's going to be important because eventually, like I said, we are going to use another method of going backwards and splitting this FOIL method apart. In other words, it's called factoring because you're splitting it into factors. But these two factors make what we call intercept form. There are some real-world situations where you use things that are similar to that, similar factors for intercept form. And here's kind of an example of using those factors to create the quadratic and intercept form. And then we can also multiply them to get standard form. The number of items a company sells frequently is a function of the item's price. What that means is if you're selling something, if you raise the price, you could lose sales. If you lower the price, you could gain sales. But there is a function there, meaning there's a certain kind of relationship between the price and the number that you sell. And that also creates another relationship called revenue. Revenue from the sales of an item is the product of the price and the number sold. This is something that'll benefit you well if you know this particular little saying. Revenue, basically, is equal to price times number sold. Now, there's a reason I put those in parentheses like that, because essentially those little factors, like we talked about in intercept form, is the way these problems are set up. And we will also see this in some physical things like area. So in this particular problem, I have revenue for a unicycle company. Yeah, you're going to sell unicycles when you grow up, right? I know I wanted to. No, I'm just kidding. Seriously, guys, it's kind of a goofy example. But it says the number of unicycles a company sells can be modeled by negative 2.5p plus 500. So that's the number they sell, P being the price. Now, some of you may be thinking, oh, what in the heck does that really mean? So I'm going to move this over here and kind of do a graph right here beside it. Remember that mx plus b thing we talked about? That means up here at 500 and then going down 2.5 over 1, you're going to get a line that describes this negative 2.5p plus 500. What happens to the number of sales if the P is the price? So if we jack the price up, the sales go down. If we lower the price this way, lower the price means go this way, the sales go back up. Now, some people would be tempted to say, okay, I'm going to go straight up here. I'm going to go to that point. The problem is with that point, the price is 0. That means you're going to make $0. Some people may say, okay, well, I want to go the opposite way. Well, around here, if you go down here, this point down here would also be $0 because you would not be selling any. We want to kind of find a happy medium in here. And the way we figure it out is not actually on this linear graph. The way we figure it out is, okay, I want to find the price times the number that we sell, the revenue, when that will be a maximum. Not just when the price is the best or when the number sold is the best, but both at the same time. And so what we look at is we look at a function that price is P, and the number that we're selling is this negative 2.5P plus 500. That's the number that we're selling. So guys, what I want you to realize here is that when we are looking at this right here, somebody did some studying to figure this out. Somebody in the company didn't just come up with that equation out of nowhere. They actually did some studying with the price and saw what happened when they raised the price and when they lowered the price. This didn't happen just by randomness. What it probably was they figured out, okay, if I jack the price up to here, here's a point. That's how many we sold. If I lower the price, this is how many we sold. If I jacked it back up again, this is how many we sold. Lowered it again, this is how many we sold. And they get this scatter plot. In this scatter plot, they draw a line that fits the best. We call that the best fitting line. And so then they said, okay, now I know that that's how our sales react to our price. So now what we can do is we are going to look at this in the next section when we start talking about graphs, is we could figure out what the maximum revenue is. Now we are going to talk about also, like I said, the fact that you could multiply this together and put it into standard form. So you're going to see that it's negative 2.5p squared and then 500p. That is a quadratic. Notice it doesn't have a number here, because the revenue would start at nothing. You're not going to just start with magical revenue in your bank account. You will start with nothing, because if you don't sell anything, you don't get anything. And so we'll talk about then how this will be maximized. Notice it has a negative number. That means it's going to be opening down. You can do the same thing with something like this. Let me zoom in a little bit here. You maintain a music-oriented website that allows subscribing customers to download audio and video clips of their favorite bands. When the subscription price is $16 per year, you get 30,000 subscribers. So right now, if you think about it, the revenue is equal to $16 times 30,000 subscribers. That's $480,000. Now that sounds really good, but if I'm a business person, I always want to make more, or maybe not always just greedy want to make more, but I could use more money to make my company better, and then maybe even get more subscribers on top of that and make more money. So it could be a good cycle if I could make more. And so what you do is you do a little bit of studying. Again, like I said, like the unicycle company, you study what's happening. Each $1 increase in price, you expect to lose 1,000 subscribers. So think about this. Think about the beginning amount and what it's moving by. If I know the price is $16 and I'm moving that by $1 increase, that's MX plus B. That is the beginning amount of 16 and I'm moving by $1. The number that I'm selling follows the same kind of pattern. You have 30,000 people right now at $16. But if you move it up $1, you're going to lose or move down 1,000 people. So this X actually represents for us what happens if I jack the price up by $1. The number that I sell is going to go down by 1,000. Well, what if I did $2? $2,000, $3, $3,000, $4, $4,000. And some of you may say, well, why don't I just do that, Mr. Harrison, and just figure out what it would be? Well, actually what happens is sometimes it doesn't end up on an even dollar. Well, I'll start plugging in decimals, Mr. Harrison. Yeah, but you realize how many you might have to plug in? I'm going to show you a way to find the maximum for this without having to go through and do all that plugging in and chugging. You know, plug and chug, just doing all kinds of math with calculator, when you could do some real quick stuff and get the answer a lot quicker. So I'm going to show you how to do that next time. All right, so that gives us quadratics. Again, you could multiply these things together like you did earlier back over here with the FOIL method, and it would put it into that standard form. And we're going to show how the standard form ties back with vertex form a little bit later as well. All right, so let's look at one more little example, and then I will let you go for this lesson. This is an example, let's say, that you're doing at your house. You have a dog pen that measures 4 meters wide by 6 meters long. So right now you have this dog pen, 4 meters, 6 meters, right? Now I'm going to go ahead and warn you, this is a simple example, but I'm using it to give you a more general principle that you'll see with these types of things. You want to double the area of the pen by adding the same amount of fence to the length and width of the pen. So essentially what we're happening here is we got one dog right now in here. But now we want to get 2 dogs, and so we want double the area. So we want this area to be double. Notice that this picture is probably not drawn to scale, meaning it's not an accurate picture of what that actually is going to look like in shape. But I know I'm going to add some length this way and add some length this way to make my pen bigger, double the amount of area. What's the area right now? The area right now is 4 times 6, length times width, right? It gives me 24 meters squared, right? So right now it's 24. Later on, when I double the area, I want it to go from 24, which it is right now, 24 meters squared. The new area, I'm going to put A sub n for new. I want that to be 48 meters squared. That's what I want it to be. But I need to know, what do I need to add to this side and what do I need to add to this side to make it work? Well, think about what area is. Like I said, area is length times width. So that was 4 times 6 equals the 24, right? Well, look at the bigger area now, the 48. It's not just 4 times 6. It's 4 plus something. I don't know what that answer is yet. Now, some of you are saying, I know. Guys, remember, I'm giving you a basic example to show you the concept behind it before we actually do some harder ones later. So 4 plus x. And the length here is 6 plus x. Now, what could happen is I could add the same thing around the whole thing instead of just one side here and one side here, and it makes things a little bit more complicated then. But this is the length times the width equals 48. And this equation is that intercept form. And we're going to go and we're going to talk about how I would actually solve this later in the chapter. So, when you look at something like this, I don't like this. This is not a perfect example, but we'll use this one. This one's going to be okay here. So this is a stained glass window. And if you have a stained glass window, you typically have a window frame. This one is going to be a border around this of clear stained glass before I get into the frame. And so what you have is essentially a shape like many of you have seen here. A stained glass window. Let me see if this will work here. Oh, not that. That was a dummy move, wasn't it? Let's try this. There we go. Essentially, I'm going to create this border around this stained glass window, and it's not going to be perfect. I was trying to make it as even as possible, but I kind of messed up just a little bit. But you have this even border all the way around it. What that means, notice, is that if this stained glass right here is 2 feet across and 4 feet down, I'm going to add on this side and this side, not just 1x like we did in the last problem, but I'm going to add 2 x's to it. So that is the beginning amount plus what it's moving or changing by. Notice this side, I'm going to add something here and add something here. So instead of just 2 plus x, like we did in the last problem where you just added to one side of your dog pen, you're doing the beginning amount 2 plus 2x. And you could make it even more complicated if you wanted to go into a swimming pool and maybe you had your, and it's going to be an ugly drawing here, but you got your swimming pool, and then you want to add concrete all the way around it, but up here you want to make this side of concrete 3 times as big. So this could be X, but this could be 3X, because I want to put some chairs over here or a nice little outdoor grill area or something like that. It's the same concept, because what you're doing is your length times your width. Guys, that sets up these parentheses like that intercept form. Now this one has a little bit more tricky stuff here, because you are going to have to realize that if I have 7 square feet of clear glass to create a border, that means this whole rectangle, I have to subtract out the area of the middle, the 2 times 4, and that's going to be equal to 7 once I get done, because I only have 7 square feet, of clear glass. The 2 times 4 is the actual stained glass in the middle. So I need to take that away from the rectangle, which includes everything, before I set it equal to how much I have, and so how much I can actually make the width of the border be. Now, we're going to talk about that, like I said, when we get into the later parts. Today, what we've done was we have just learned how to set up and write some quadratic equations. Some of them are a little easier than others. Some of them are given more information to you. Some of these you have to do a little bit more thinking on your own. You have to think physically, like in these area problems, or you have to think sort of figuratively, like the revenue problems where you're adding $1 but losing people. You got to think about those things being like the mx plus b that we did in the linear thing. But then you've got 2 parentheses, because in area you've got length times width. In revenue problems, you've got problems where you have the price times the number sold. But each parentheses here represents a beginning amount and something moving or changing. And that gives me some equations that are quadratics. So, basic quick review before I shut my mouth. You've got standard form of a quadratic. You've got vertex form of a quadratic. Remember, it's called vertex form because opposite of this and the same as this number is your vertex. And you've got intercept form. Intercept form is this little form, again, that has the 2 parentheses. And these 2 factors are going to be things that help me with the intercepts of a graph, specifically the x-intercepts. But it's also the way you see a lot of setup for area problems and revenue problems. So these 3 forms of quadratics are the way that we write them. The next video, we're going to go through how do we take these quadratics and graph them. And we're going to go through all 3 forms of these with graphing quadratic equations on the next video.